1, 2, 3, 1, 2, 3. Let me check. This is Introduction to Information Theory, problem solving session number 6. I'm your TA Sachin from the Indian Institute of Science. As usual, we'll solve 10 MCQs based on the content covered in week 6 of the course. Question 1. Which of the following statements is correct? If Xn and Yn are typical sequences, then Xn Yn is jointly typical. Option B, if X and Yn is X and Yn are jointly typical sequences, then Xn is a typical sequence, but Yn may not be a typical sequence. Option C is if X and Yn are jointly typical sequences, then Xn and Yn are also typical sequences. Option D is similar to option B. Except that in option B says if X and Y are jointly typical sequences, then Yn is a typical sequence, but Xn is not a typical sequence. Which of these following statements is a correct statement? This follows directly from the definition of a typical sequence of jointly typical sequences. So by definition, if X and Yn are jointly typical, then Xn should be a typical sequence. Yn should be a typical sequence. And additionally, uh, the empirical joint entropy should be equal to the true joint entropy. So, any jointly typical sequence need to satisfy uh, three properties, which first two properties require xn and yn to be typical sequences by themselves. That's directly from the definition. So the correct statement among these is option C. The second question is as follows. If rate R is achievable, there exists sequence of codes with following parameters such that the maximal probability of error lambda n tends to 0 as n tends to infinity. So for P, the code is has 2 per nr code words and code word length n. The code Q has 2 power nr minus 1 code words and length n. And the code R has 2 power 2nr minus 2r code words and length n minus 1. Which of the parameters are correct? So what the question is asking is, they've given you one fact, that is R is achievable. That means the capacity must be greater than R. Otherwise R wouldn't be achievable. Then they're telling you that you have three different codes with different parameters. So for each of these parameters, you could calculate the code rate. Then they're asking you which of the three codes has a rate which is also achievable. Or in other words, which of the parameter sets PQR gives you an achievable rate. The options are only P, option B is only Q, option C is both P and Q but not R, option D is all of them. So we say a rate R is achievable if there exists a sequence of codes with parameters seeding of 2 power nr, comma n, such that the maximal probability of error lambda n tends to 0 as n tends to infinity. That's what R is achievable means. But also in the lecture we saw that uh, the rate of a code with parameters m comma n is given by, let's say, call it r dash log of m by n. Log is to base 2 bits per transmission. So using that formula, we can calculate the rate of each of the codes PQR. So the rate of the code P is log of, there are 2 power nr messages in code P and message length, code length is n. Log of 2 power nr is nr divided by n is r. So P has the rate r, then rate of the code Q is log of 2 power nr minus 1 divided by n. This is nr minus 1 divided by n. This is r minus 1 over n. This is less than r. And rate of the code S is log of How many code words are there? 2 power 2nr minus 2r divided by n, which is 2nr minus 2r by n. It's 2r minus 2r over n. The length was actually n minus 1. So we'll have to leave it at that. Then you can take 2r common, you will be left with n minus 1 by n and so on. So the rate is 2r is greater than r. So since rate r is achievable, that means capacity is the supremum over all achievable rates. So if some rate is achievable, then the capacity that rate must be less than or equal to the capacity. So if some other rate r dash is less than an achievable rate r, that other rate r dash is also less than the capacity, which means that rate is also achievable. So Shannon's coding theorem says if rate is less than capacity, then it's a achievable code, and its converse says that if rate is greater than the capacity, then it's not achievable. So we can say if rate r is achievable, then for all rates r dash less than or equal to r dash is also achievable. But for some r double dash greater than r double dash may not be achievable. We don't know. We can't give any guarantees. That's it. It might be achievable if capacity is greater than r and r dash is between r and the capacity. But it may not be achievable. So we can't say that all of them are definitely achievable, and both P and Q are achievable. So the correct answer is option C, both P and Q, but not R. Question 3. If information bits from a binary symmetric source are sent at rate r is equal to 3 via a discrete memoryless channel of capacity C is equal to 2.5 bits per use without feedback, then bit error probability at the receiver is lower bounded by A 0.129, B 0.2, C 0.5, D 0.1. So the formula for this was done in class from the lecture. I can give you the slide maybe if you want to refer. 10, let's say 10B. Right after the converse of converse to noisy code, channel coding theorem, slide 15, I think. Okay, we can refer to this. For a if information bits from a binary symmetric source, right, as BSS, are sent at a rate R via a DMC of capacity C without feedback, then the bit error rate, bit error probability at the destination, that is the receiver, is lower bounded by PB greater than equal to H inverse of 1 minus C over R if R greater than C. And for our question, here R is 3. We're sending it at 3 bits per use. capacity is 2.5 bits per use. So PB is greater than or equal to H inverse of 1 minus 2.5 by 3, which is 0.129. So first thing to note is that they're asking for a lower bound. It will be some lower bound that has been taught in the lecture. So even if other lower bounds exist, uh, unless it has been done in the lecture, you shouldn't use other lower bounds. Second thing is if to find H inverse, unless it's a straightforward calculation, if it's from a table or something like that, then the value will be given to you if it's during an exam or something. If it's during an exam, otherwise, if it's if it's for an assignment, then you can probably look it up on the internet. Point 129 is option A. Question 4. For independent Gaussian random variables x1, x2, etc. n random variables xn with possibly different means and different variance. The statement h of x1 plus x2 plus etc. plus xn divided by square root of n is greater than or equal to 1 over n summation h of xi I is equal to 1 to n. Option A is always true. Option B is always false. Option C is sometimes true and sometimes false. Option D is equality always holds. x1 plus x2 plus x3 etc. to xn is a sum of Gaussian random variables. And sum of independent Gaussian random variables. So in that situation, their sum is also a Gaussian random variable. So sum of independent Gaussian random variables is also Gaussian. And for a Gaussian random variable, what is the entropy? So from that we can write the differential entropy of the sum divided by the square root of n is half log of 2 pi e, uh, the variance square, and for sum of Gaussian random variables, the variance square is the sum of the variances, and there's a factor 1 over square root n, which will contribute 1 over n to the variance. So that part comes from probability, and the details you'll have to work it out yourself. Finding the variance of a sum of independent random variables. And then the differential entropy was should have been taught in class for a Gaussian random variable. It's half log of 2 pi e sigma square, where sigma square is the variance. Now, individually, if you take them and sum them up, 1 over n, the RHS is 1 over n summation of h of I is equal to 1 to n, and each of the xi's is a Gaussian random variable, and the differential entropy is half log of 2 pi e sigma I square, and so the summation, you can take the half outside, and 1 over n times summation of log 2 pi e sigma I square. So the sum of log is the log of products. So we can write this as half n log of product of 2 pi e sigma I square I is equal to 1 to n. And you can take the 1 over n inside the log and write it as 2 pi e product of sigma I square to the power 1 over n. Now, since arithmetic mean is always greater than or equal to geometric mean, we have the arithmetic mean of the variances squared is sum of sigma I square I is equal to 1 to n divided by n. That is greater than or equal to the geometric mean is product of sigma I square I is equal to 1 to n to the power 1 over n. That is the nth root of the products. So log is an increasing function. So you can take log on both sides, and the inequality won't change. Therefore, log of sum of sigma squares will also multiply both sides by the factor 2 pi e, which will give you 2 pi e times this is greater than log of 2 pi e times product I is equal to 1 to n sigma I square or 1 over n. Then you can multiply both sides by half. But what is the quantity on the left hand side? That is h of x1 plus etc. xn divided by square root n, and the quantity on the RHS is 1 over n summation of h of xi I equal to 1 to n. Therefore, the statement is always true. So option A is correct. Question 5. Entropy of a 3-bit uniform quantization of a random variable distributed uniformly as u of 0, 1 over 8 is approximately given by option A 3 bits, option B 0 bits, option C minus 3 bits, option D minus 1 bit. We have the entropy of an n-bit quantization of a continuous random variable x is approximately given as h of x plus n bits. For a uniformly distributed random variable with the distribution u of a comma b, we have h of x is log of b minus a bits for b greater than a. So here n is equal to 3, b is equal to 1 over 8, a is equal to 0. Therefore, h of x is log of 1 over 8 minus 0, which is minus log 8, which is minus 3, and entropy of the quantized random variable is approximately equal to h of x plus n, which is minus 3 plus 3, which is 0 bits. So the right answer is option B. We are halfway through the session, so I'll take a small break and come back. I'm back. Question 6. Which of the following statements are true? A. H of x equals minus infinity implies h of ax equals minus infinity for some constant a. B. H of x greater than 0 and h of y greater than 0 implies h of xy greater than 0. Option A, only statement A is true. Option B, only statement B is true. Option C says both A and B are true. Option D says both A and B are false. Solution, we know that h of ax is equal to h of x plus log mod a. Therefore, h of x equals infinity implies h of ax equals a minus infinity. Therefore, statement A is true. Then, A is true. B is false. For that we'll give counter example. So consider a random variable y which is x plus z, where x is distributed according to the normal distribution with mean 0 variance 1. Z is distributed according to the Gaussian distribution with mean 0 variance e. Let x and z be independent random variables. Now the joint differential entropy h of xy is h of x h of y given x is h of x such h of y is x plus z given x, which is h of x plus h of x plus z given x is same as h of z given x. So this is h of x plus, since z and x are independent, h of x plus h of z. X is a Gaussian normal, x has normal distribution, mean 0, variance 1, so its differential entropy is half log 2 pi e sigma square. Sigma square is 1. For z, sigma square is epsilon, so it's half log 2 pi e epsilon. Now we have h of x greater than 0, h of y so h of x is half log 2 pi e, which is greater than 0. H of y is half log 2 pi e into 1 plus epsilon. So remember this previous question where we had calculated the differential entropy of a sum of Gaussian random variables, except that we had a factor 1 over square root n. If we don't have that factor, then if we have that factor, then this is the entropy. If you don't have 1 over square root n, then we won't have 1 over n here. So h of x1 plus x2 is nothing but half log 2 pi e sigma 1 square plus sigma 2 square. Sigma 1 square in this case is 1 and sigma 2 square is epsilon, so it's h of y is half log 2 pi e into 1 plus epsilon. Since 1 plus epsilon is greater than 1 and 2 pi e all are greater than 1, their product is also greater than 1, so log of that is greater than 0. Half log of that is also greater than 0. So both h of x and h of y are greater than 0, but h of y, so x comma y approaches negative infinity as epsilon approaches 0. So there are values of epsilon for which we can make h of x comma y less than 0. So B is a false statement. Therefore, only A is true is the right option. The option A. Question 7. Consider the following statements for any xy continuous random variables. Statement A says ixy greater than 0 implies h of xy greater than 0. Statement B says h of xy greater than 0 implies ixy greater than 0. Again, is which of these statements is true? Is only A true? Is only B true? I guess I can copy the options from previous question. Are both A and B true? Or are both A and B false? Solution, again, we'll give examples to show that both statements are false. For A, counterexample is this. Let x be distributed as n of 0, comma 1, z be distributed again as n of 0, comma epsilon, y is x plus z, since z are independent. Then ixy is h of y minus h of y given x. Is h of y minus h of z plus x given x. So h of y minus h of z given x, which is h of y minus h of z, as x and z are independent. So this is half log 2 pi epsilon minus half log 2 pi, half log 2 pi e minus half log 2 pi e epsilon. And as epsilon approaches 0, I of xy approaches infinity. So I of xy is greater than 0. There are values of epsilon for which I of xy is greater than 0. But you consider h of xy, it is half log 2 pi e plus half log 2 pi e epsilon from Q6, from the previous question, from the solution to the previous question. So h of xy approaches minus infinity as epsilon approaches 0. So as we get closer and closer to 0, as epsilon gets closer and closer to 0, h of xy is negative. So there should exist, there will exist some value of epsilon is close enough to 0 such that I of xy is positive and h of xy is negative. So I of xy is positive does not imply that h of xy is positive. For B, consider the counter example. Let xy be independent and identically distributed with normal distribution with mean 0, variance 1. Then I of xy is 0, but h of xy is h of x plus h of y given x. So h of x plus h of y, since they are independent, which is 2 times half log 2 pi e to log of 2 pi e is greater than 0. H of xy is greater than 0, but I of xy is 0. So B is also false. Therefore, both A and B are false. We have shown that through counterexamples. Question 8. Let x1, x2 be a multivariate normal distribution with mean vector 1 and covariance matrix k given by 1, 0.3, 0.31. Then h of x1, x2 is approximately given by option A 1.943 bits, option B 2.305 bits, option C 2.972 bits, option D 4.026 bits. For a multivariate normal distribution with mean mu and covariance matrix K, the joint entropy H of x1 to xn, joint differential entropy, this H of the distribution with mean mu covariance matrix K is half log of 2 pi epsilon for n mod K, where mod K is the determinant of the matrix K. So determinant of 1, 0.3, 0.31 is 1 minus zero point 0.9. Sorry, 1 minus 0.09, which is 0.91. N is equal to 2 for h of x1, x2 is half log 2 pi square into 0.91. If this is approximately half log 265.5 is approximately half of 8.053 is approximately 4.027, 4.026. So the right answer is option B. Question number 9. Which of the following statements is incorrect about differential entropy? H of x can be greater than 0 or less than 0 or equal to 0. H of x given y less than or equal to h of x. H of x1, x2, etc. xn is greater than or equal to h of x1 plus h of x2 plus etc. plus h of xn. D. None of the above. So option A is true. This is differential entropy, which is entropy for continuous random variables, which can be greater, less than, or equal to 0. In case of discrete random variables, there is the entropy is always non-negative. That's not true for continuous random variables, and we saw an example of that in the previous questions. When we are giving counter examples for question 6 and 7, we gave an example of so h of xy was going to minus infinity as a epsilon went to 0. So xy, you can take that a random vector as a random variable z. So z is the random variable or random vector xy. So that random vector is also a random variable distributed according to the joint distribution of x and y, the intensity function x and y. So what I mean to say is each random vector can be taken as a random variable, and then the entropy of that random variable is negative for values of epsilon close to 0. So entropy can go to negative values. Second statement saying that conditioning reduces entropy is true for differential entropy also, similar to the entropy for discrete random variables. So the third statement is false because the second statement is true, third statement is false. So we can write h of x1, x2, xn using the chain rule as summation h of xi given xi minus 1 to x1, and since conditioning reduces entropy, it, this is less than or equal to summation of h of xi equal to 1 to n. But option C says h of x1 to xn is greater than or equal to summation of h of xn. So C is the false statement. Last question. Which of the following statements is true for continuous random variables xy? Option A, h of x equals 0, h of y equals 0 implies ixy is 0. Option B, ixy is 0 implies x and y are independent. Option C, h of xy equals 0 implies I of xy equals 0. Option D, none of the above. Again, to show some statement is false, we'll mostly use counterexamples. Let xz be independent Gaussian random variables distributed as n of 0, 1 over 2 pi epsilon. Let y be half x plus root 3 over 2z. Y is distributed according to n of 0 over 0, 1 over 2 pi epsilon. We have h of x is h of z, h of y is 0. But I of xy, which is h of y minus h of y given x, is 0 minus h of root 3 over 2z, which is minus h of z minus log root 3 over 2 is greater than 0. Because log root 3 over 2 is a negative quantity, minus of that is greater than 0. Therefore, A is false. I of xy equals d of f of xy parallel f of x, f of y equal to 0 with equality you can only if f of xy equals f of x, f of y almost everywhere, which implies xy are independent. Therefore, B is true. And we have let xy be such that x is distributed according to u of minus half comma half and f of y given x of y is y distributed as 0 comma 1 if x greater than or equal to 0, y distributed as u of minus 1 comma 0 if x less than 0, and f of fy is integral of f of y given x of y to fx of x, which is u of minus 1 comma 1. Therefore, h of y is log 2, which is 1. So for the uniform random variable u of a comma b distributed as u of a comma b, h of x is log of b minus a. We saw that in one of the previous questions. Therefore, h of y is log of 1 minus minus 1, which is log 2, which is 1. H of x comma y is h of x plus h of y given x. But h of x is 0 and h of y given x is 0. So h of x comma y is 0. But I of x comma y is h of y minus h of y given x is 1 minus 0 is greater than 0. So option C is also false. H of x comma y is 0, but I of x comma y is greater than 0. C is false. Therefore, the right answer is option B. If I x y is 0, then x and y are independent. That's it for today. See you next week.